Swayam Prabha. Digital India. Educated India.
Welcome to lecture 9 of mechanics of materials. In the last lecture we saw about different states of stresses, uniaxial state of stress wherein the stress is applied only along one direction. For example, this bar being pulled like this is an example of a uniaxial state of stress. The next state of stress that we saw was a biaxial state of stress wherein the stress was applied on two orthogonal directions. Basically you can pull like this and pull in this direction also. Next state of stress that we saw was a pure shear state of stress, that is we said that if there exists a plane in which there are no normal stresses but only shear stresses are present, that is called as a pure shear stress. Even in that state of stress there will be a plane in which there is no shear stress but there are normal stresses alone. Okay, that will be the principal direction of the along the principal planes there will be only normal stresses and no shear stresses, even though the state of stress is a pure shear. Then we saw what is called as an hydrostatic state of stress wherein any plane in the body won't have a shear stress coming in that plane. Okay, that is called as an hydrostatic state of stress. The next state of stress that we saw was a deviatoric state of stress wherein the stress won't have a volume change but there will be only a distortion changes in the body. It will distort the body as like a pure shear state of stress wherein it is a traceless tensor, so that tensor is called as a deviatoric state of stress. Okay. We also went ahead and looked at 3D stress analysis. Okay. We defined the normal stress as the traction component of the traction acting along the normal direction to the plane. Okay. That is called as the normal stress. The component of the traction acting parallel to the plane is called as a shear stress, and we found the expressions for the normal and shear stress to be given as written in here. And we also said that we are interested only in the magnitude of the shear stress, and hence you can compute the magnitude of shear stress from the expression given in here. And then we went ahead to maximize the normal stress. In other words, we were interested in finding the plane on which the maximum normal stress occurs and what is this value of the normal stress. That maximization problem led us to two equations wherein we want sigma n equal to lambda times n and n dot n must be equal to 1. For first equation to have a non-trivial solution, non-trivial n, we require the determinant of sigma minus lambda identity should be 0. This will result in a characteristic, what is called as a characteristic equation, which will be given by a cubic polynomial of the form minus k1 lambda square plus k2 lambda minus k3 equal to 0. This is called as a characteristic equation where k1 is trace of sigma, k2 is 1 half trace sigma squared, trace of sigma square minus trace of sigma square, and k3 is determinant of sigma. Okay. Now these k1, k2, k3 are what are called as the invariants of the stress tensor. In other words, these quantities does not change with what coordinate system you use to represent the stress tensor. Okay. By solving this cubic equation you will get 3 real roots. Because sigma is a symmetric tensor, you are assured of 3 real roots. Those 3 real roots are denoted by lambda 1, lambda 2 and lambda 3. Those 3 real roots are denoted by lambda 1, lambda 2, lambda 3, and the corresponding directions obtained by solving this equation sigma n equal to lambda I of n would be n1, n2 and n3 corresponding to lambda 1, lambda 2 or lambda 3 that was substituted for lambda. These are called as the principal directions. Okay. Now we will go ahead and we will see a bit more of how to represent the stress in the principal directions, and then we will find what is the maximum shear stress that will occur and what plane it occurs, and then we will define what is called as the octahedral stress, the stresses on the octahedral plane, the normal and the shear stresses, and then we will go and look at equilibrium equations which the stress field has to satisfy. Okay. This stress tensor was add some representation sigma xx, sigma xy, sigma xz, sigma xy, sigma yy 0, sigma xz 0, sigma zz. This was a 3 dimensional stress state in some chosen coordinate system x, y and z. Ex, Ez. In this coordinate system, this was the representation for the stress. Okay. Now, what I can do is I can change the coordinate system and I can write the same stress tensor in the coordinate system given by n1, n2, n3, the principal directions. Okay. Now, I can use the principal directions as a coordinate basis, because I know that the principal directions will form an orthonormal set. By virtue of the stress tensor being symmetric, we know that the principal directions would be orthonormal since stress is symmetric. Sigma is a symmetric tensor. We have been using this, we have to show this when you look at the equilibrium equations. Okay. Now, this was in Ex, Ey, Ez basis. Now, if I represent the same stress tensor in n1, n2 basis, this will be sigma 1 n1 tensor product will be sigma 1 n1 tensor product n1 plus sigma 2 n2 tensor product n2 plus sigma 3 n3 tensor product n3, right. Because what happens is I am writing it in the principal direction basis, so that will be having this representation. Okay. Now, if I were to represent this in a matrix form, this sigma would be of the form sigma 1 0 0 0 sigma 2 0 0 0 sigma 3. Okay. Because there exists an orthogonal matrix which connects Ex, Ey, Ez to n1, n2, n3. Okay. Because both are orthonormal sets, you are assured of a transformation matrix that will do that. Okay. Now, we can define an orthogonal matrix Qij, which is Ei dotted with Nj matrix. Okay. Then I can get my sigma in the matrix form of sigma in Nj basis obtained as this Q transpose sigma in Ei basis times Q matrix. Okay. This will give me this diagonal representation of the stress tensor. Okay. So, now having obtained the diagonal representation of the stress tensor, next what we want to do is find what is the maximum shear stress that will occur and what plane it will occur. Okay. So, I am interested in find the maximum shear stress and the plane on which it occurs. Okay. Now, the maximum shear stress expression tau max or the shear stress expression is given by norm of traction acting along a particular normal squared minus sigma n squared. Okay. So, let us deal with the representation of the stress in the principal directions. So, let us assume that m is the normal to the plane on which maximum shear stress occurs. And m is given by m1 n1 plus m2 n2 plus m3 n3 such that m3 is square root of 1 minus m1 square minus m2 square. Okay. Now then you can find what is the shear stress acting on that plane n. Okay. The shear stress on this plane would be tau of m squared would be sigma 1 m1 n1 plus sigma 2 m2 n2 plus sigma 3 m3 n3 norm of this vector squared minus the normal stress acting on that plane, which would be sigma 1 m1 square plus sigma 2 m2 square plus sigma 3 m3 square. Okay. Now this is nothing but sigma 1 whole squared, this is sigma 1 m1 squared plus sigma 2 m2 squared plus sigma 3 m3 squared minus sigma 1 m1 square plus sigma 2 m2 square plus sigma 3 m3 square the whole square. Okay. That is tau of m square. Okay. Now what I want is I want to find m1 and m2 such that find m1 and m2 one as maximum value. Okay. This would imply that I have to set dou T m squared by dou m1 to be equal to the derivative of the shear stress magnitude by dou m2 to be equal to 0. I will get two equations involving m1 and m2 which I have to solve. I have to use here the fact that m3 is given by this expression in here, okay, and I have to solve for m1 and m2 from these two equations, wherein I will get that m1 is plus or minus 1 by root 2, m2 is plus or minus 1 by root 2 and m3 is 0. Okay. Or I can get another set of solution, this being a nonlinear equation there will be more than one solution. So, 1 by root 2 0 plus or minus 1 by root 2 or 0 plus or minus 1 by root 2 plus or minus 1 by root 2. These are the possible solutions that I will get. Okay. If I know that if sigma 1 is greater than sigma 2 greater than sigma 3, if greater than sigma 3, then I will get the solution which is given here. This will be the tau max solution. The direction will give me tau max. Otherwise, I have to these are the possible 12 solutions which I have to substitute in the expression 1 and find tau max corresponding to those 12 solutions and then pick which one gives me the maximum shear stress. Okay. If I assume that this is the case, then I know that the solution would be, this will imply m1 is plus or minus 1 by root 2, m2 is 0 and m3 is plus or minus 1 by root 2. Okay. Then T m squared would be equal to tau max would be, then T m is equal to magnitude of T m equal to tau max would be 1 half of sigma 1 minus sigma 3, okay, sigma 1 minus sigma 3. Okay. In general, if I do not have these specifications, I will write tau max as 1 half maximum of absolute value of sigma 1 minus sigma 2, absolute value of sigma 2 minus sigma 3 absolute value of sigma 1 minus sigma 3. Okay. Now, this corresponds to this case in here, sigma 1 minus 3 corresponds to this case in there, and this corresponds to this case in here. Okay. So, depending upon which set you will get one of the solutions here. Okay. I am not going to do the algebra here, you can look up advanced solid mechanics in NPTEL notes for going through the detailed algebra, okay, in the web course. Okay. Now, what is the direction or what is the plane on which this maximum shear stress occurs is the next question we want to answer. So, we found M1 to be plus or minus 1 by root 2 plus or minus 1 by root 2 as the solution, which means M would be plus or minus 1 by root 2 N1 plus N3 in this specific case when sigma 1 is greater than or equal to sigma 2 greater than or equal to sigma 3. Okay. So, there are 4 possible planes here, the 4 possible planes in N1 N3 coordinate system is this is N1, no, say this is N1 and this is N3. The possible planes are making 45 degrees with respect to each. These 4 planes are the planes on which the maximum shear stress occurs. Okay. So, tau max will occur like that, or it can be occurring like this also. Okay, because you know only the magnitude of the tau max, you are finding the maxima is the square of the tau max. So, it can occur in either direction. Okay. Now, you will find that this normal here is given by N1 plus N3 by root 2, whereas this normal in here is given by minus N1 plus N3 by root 2. This normal in here is given by minus N1 plus N3 by root 2, and this normal in here is given by N1 minus N3 by root 2. Okay. Now, all these 4 normals gives you the same tau max, because tau max will occur in pairs, complementary shear stresses are to be same, sigma xy is same as sigma yx, and hence you get these 4 normal planes. Okay. Now, having for the maximum shear stress, next I am interested in defining what is called as an octahedral plane.